I think maybe one of the questions that I was hoping we could start off with is just whether, in the discussions over the past 24 hours, we've heard from, like as you said on that last slide, the experimentalists, the theorists, and the neuroscientists, and the engineers. And I was just wondering if, in sitting through the talks, if anyone heard any principles from one of the domains that they don't currently work in that they thought would be relevant to their domain. Whether there's any information transfer from all of us having sat in this room, or did we just hear the parts that we already knew and then just sort of filtered out all the other stuff? So I know that's a hard question to answer, but I think it might be a good way to start off the panel, and then just take the questions.
Well, I'm not sure if this is exactly transfer you have in mind, but the wafer scale systems being built in Europe were very surprising and impressive to me, and very interesting to me, and it justified my flying out from Boston for sure, just to hear that one talk.
Well, I guess I have a question about how approximate computing has, what lessons you've learned about the principles that allow approximate computing to give gains in speed and efficiency, and where is the connection with the brain, right? It's clear that the neural components are noisy, and it's very plausible that the brain does a lot of, approximate computing. But what can we learn from engineering to the brain about approximate computing? Where do you think the connections are?
Well, yeah, so, as I mentioned, the work I ended up doing was inspired by some of Carver Mead's ideas, and obviously, this is a very interesting engineered or not engineered system that I drew from. I've learned that a lot of software does not need the kind of machines that we have traditionally built. I am hopeful that if this work goes forward and people are writing code, the other hardware engineers will realize, I don't have to build things that run Windows necessarily or always, and that there will be proliferation of new kinds of computing architectures that based on this approximate work. And then, of course, I hope that if we had, say, a billion-core machine that was compact and not too expensive, and you could have one in every university, that might enable the kinds of experimental, computational experimental research that would accelerate the work in neuroscience.
But
so let me make an observation here. So all computing is approximate computing. It's interesting how people sort of come up with new names for old things periodically, and approximate computing is one of these. So at one point in time, I worked on radar front ends. They're 4 bits, right? Because that's the SNR you have coming off the antenna. And all signal processing systems are highly tuned to the number of bits that you need to represent the data. And it's approximate, right? All computing is approximate, right? We don't have an infinite bit representation for stuff. Now, the reason why everybody uses single or double precision floating point numbers is because they're lazy, right? If you actually think about how many bits you need to represent something and want to accurately model the error and see if you're getting the wrong answer, it requires a lot of work. And what pushes people to go to more approximate representations from the less approximate representation of 32 or 64-bit floating point numbers, the desire for speed and efficiency. But people have been doing that since as long as there have been computers. In fact, they did it more in the early days of computing when things were more expensive. And I think that what's interesting about neural networks is numerous studies people have done on precision indicate that you need very few bits. In fact, some people have done studies showing that you can get by with 1-bit precision for these networks.
Right, and I agree, of course, in the 50s, analog computing and early analog computing and early digital computing. I think that it's, as a programmer, the surprise to me is that I can be almost as lazy using pretty low quality arithmetic and get good quality results, and that has been a surprise to me, and I think relevant.
So I was a little confused by the power efficiencies that you were able to get from that work. So clearly using lower precision is part of that, but as we heard from Bill, it's all moving data that ultimately drives power. So I guess I missed the part of your talk where you must have described how you reduced data movement.
Right.
He didn't run a model that was big enough that he needed to pull in lots of data from off chip.
Right. I basically concluded, as everybody else has, that to first order, you can't bring stuff in off chip.
Right.
You can't do it if you want to use the inherent power of the silicon. So we put as much memory as we can with each core.
Right.
And, again, as a programmer, I can say, I'm willing to suffer. I think there are people that are willing to suffer for their
No,
goals.
but you
And
couldn't,
so,
for example, run VGGNet on that chip. There's just not enough memory to do it.
not on a single, no, this is a prototype. It was a $1 million chip. It was like a seedling, right? It's like, gosh, you got something working for $1 million? So yeah, you'd want significantly bigger chips, and if you do that, you get amounts of memory that are reasonable, especially with the kind of work that Song Han has been showing and your groups have been showing. So, but you have to give up the model of, gosh, there's a terabyte or 10 gigabytes of memory, and I can just get to it, because you can't. So fine, face it, deal with it. How hard is the programming? And my experience is not nearly as bad as I kind of would have guessed it would be.
And obviously that depends on the application.
Totally depends on the
Target
application.
applications.
Yeah.
So different question. The encoding that you think you've discovered in neurons for location, that was really cool. I thought that was really neat. Are there reasons why you would argue we should go back and reconsider how we encode numbers in computers?
Yeah, that's an interesting question. So it turns out that this solution of possibly the one thing that we don't know is whether or not the brain is actually exploiting these properties I talked about. So the properties I talked about are sort of things that you can infer from the observations of the neural response, but whether or not the brain actually exploits these properties that exist is an open question. So first of all, we don't know that the brain's
there is a number representation that's almost exactly the same thing based on the Chinese remainder theorem.
No, this is the same. Residue number
Yeah.
system is the Chinese remainder theorem-based number system. And in fact, the interesting thing is after understanding these properties of the neural system, I discovered that some hardware devices were built for signal processing applications where instead of fixed base binary number system arithmetic, they were built around residue number system arithmetic with Chinese remainder theorem because of this need to not have to carry digits over. And so because signal processing has lots of additions of large numbers, there was a hardware efficiency gain by doing it this way.
Cool.
So I think in this case, there was an independent discovery by engineers of the system, but I think if we proceed in the same vein, I think the brain might actually have insights about how to do things with very different representations than we use in conventional devices.
I'd like to hear your opinions on appropriate application domains for various levels of accuracy in these networks. For instance, to land something on the moon, you might need 6 significant figures of accuracy, but to fly a little drone around with reasonable skill, you might only need 2. I'd like to hear your thoughts.
So just one comment about that. The fact that the hardware does say, 1% error per operation does not mean that the final results need to be at that level or worse. I tried to give some examples where it was quite efficient to, iterative algorithms, I think you mentioned.
Iterative refinement.
Iterative refinement algorithms where you just quite efficiently can knock the error down, especially when you have the CPU or GPU collaborating with this kind of arithmetic. So that's a big, people expect, it's got to be worse than the hardware. Final results got to be worse than the hardware. It's not at all.
Yeah, but algorithms tend to fall into 2 categories. Almost all the neural network algorithms need really low precision because they're aggregating a lot of data and kind of summarizing it to draw conclusions. And that winds up not needing great precision at any of the intermediate steps. What needs great precision are things like certain numerical methods where you wind up taking 2 very large numbers and subtracting them from one another, and the answer is important. And there, if you don't have high precision, your answer is garbage. And so it really depends on whether you're doing these differential algorithms where you're subtracting 2 big numbers, and you care about the answer, or whether you're doing summarization algorithms where you can wind up summarizing a lot of very noisy data and getting a very accurate result.
But I'd mention, like on that FFT example I think I showed, that does do subtractions, and there are places where you get zeros when you shouldn't have gotten a zero, and then you divide by that and you get some explosion. But there were higher level places in the software where you could fix that very efficiently. So all the creativity of programming can be brought to bear in this domain, and I found that it's often surprisingly helpful. You can solve things even though it might have initially seemed like you couldn't. So I agree with Bill's point completely. It's just that there are places higher up in the software stack where things can be fixed efficiently enough to be useful.
I guess this question is mainly for Bill. It's a different thread, though. I'd be curious as to what you're seeing out there in this regard. In this community, there's a lot of interest right now in algorithms that can learn on the fly, that can deal with unstructured data. For example, we've got a robotics project where the robot has to work out its own map of its universe. And I'm curious what you're seeing. And of course, you rightly so looked at algorithms that require a lot of training and then are fixed, essentially. What are you seeing in terms of interest out there in these unstructured or less structured problems that could benefit from these?
Well, I think there's a huge amount of interest in unsupervised learning just because it's expensive to get labeled data. And so if you can have unsupervised or semi-supervised learning, it's a huge advantage because, for example, it's easy to acquire, hundreds of thousands of hours of video of cars driving on the road. It's really hard and expensive to pay lots of people in various parts of the world via Mechanical Turk to take all of those videos and label every lane marker and every sign and every car and pedestrian and bicycle and dog and cat that's in them. And so, things where it's semi-supervised, where you can label some data from previous data, or you generate synthetic models, and therefore you know the ground truth because it was a geometric model from which you generated the training data from computer graphics. Or reinforcement learning, I think, is a very popular technique where if you can simply learn, based on eventual outcome and then propagate that back to the sequence of events that led to the outcome. Those are all powerful techniques where you don't need labeled data.
And what's that going to do to your architectures, do you think?
Not very much. I think we're trying to be general enough with the architecture to not specialize it so that for at least the things we could anticipate possibly happening, we will do well on.
Thank you.
I have one question. After seeing this very nice introduction slide of Dr. Hendrickson, I wondered whether possibly this emphasis on computation power of the brain misses possibly the essence of why the brain is really so good. I don't see our brains really as a super Turing machine. I think it's extremely good in learning, I think primarily, in adapting information and also transfer learned knowledge to new scenarios. And I think one could possibly think it's an incredibly good learning machine and a mediocre general purpose computing machine then. And I think some of these questions, even about the role of spikes, would appear differently because, for example, as you know, spike is really an important aspect of simply synaptic plasticity, right? Which you wouldn't have in a spike. Is simply a certain causal chain of events, and certain causal chains are then imprinted through plasticity mechanisms, right? So therefore, one has also to reconsider the question about the role of the spike. What could it provide for learning system? And then also, I think we saw actually how much intellectual new ideas come out of optimizing now just hardware for one particular learning algorithm, deep learning algorithms, right? But we all know this is perhaps, I don't know, a few percent of the type of learning algorithms that are running in the brain then, right? So we have to now consider what is the range of possible learning algorithms, what makes them powerful, and then rethink how does the hardware support all this variety of learning algorithms.
Yeah. So clearly, in our traditional computing models, the plasticity is entirely in software, and that's not the case in the brain. And so there's this. I think that makes it hard for us. Certainly, makes it hard for me to wrap my head around what the right models are and what the right abstractions are. We certainly have, reentrant software and, software that rewrites itself, but it's not as rich as what the brain does. Clearly, the brain is doing, why am I saying this to you guys? You all know this. The brain works differently than computers do and learns differently than our best algorithms learn. I don't know. For me, what's fascinating about this meeting and the intersection of communities at this meeting is I think that there are different perspectives, different biases, different blind spots that between us, I think we can help identify and help potentially make progress on. There's no. I have two opportunities to say this now, so I'll say it a third time. I think that there are lessons that computer architects can learn from ways that the brain works and ways that the brain processes information, and we're still trying to figure out exactly what they are.
Just to follow up on Wolfgang's comment, a lot of us believe that spike trains are the fundamental data structure in the brain, and it allows reasoning about time, which as you know, in computer science is not possible. And because everything is based on a counter, there is no notion of time. And so that angle appears to us to be actually exceedingly important, in particular also when it comes to accessing memory. We don't know where memory is, but we know that it's accessed via spikes. Essentially because everything around the hippocampus is in terms of spike trains. And so to disregard this might be actually really a huge fundamental problem.
Can I ask a question about that question? Because I'm very interested. So when we say that computers can't, I'm not sure I'm quoting you correctly, so please correct me if I'm wrong. Computers can't reason about time or compute about time. I mean, of course you can write a layer of software above a digital machine that is keeping track of time, and we do that in lots of kinds of systems, electronic CAD tools and so on.
There's no program verification when you have real-time systems. It's just they're kludges.
It's just what, sorry?
It's a kludge. There's no notion of program verification when you have a real-time system. It's just not possible to be done. And there's this notion of time does not appear explicitly in a program. It does not explicitly appear, as was pointed out by Surya, in information theory. There's no notion of time.
No, but we ship real-time systems and we ship dynamical control systems
course.
that reason about time.
Yes, but they're not
correctly.
verified. They're not verified, and there's no way to actually reason about time. The notion of time doesn't appear explicitly. There's a kludge, and there's a way to deal with it, approximately. But, formally, one cannot discuss it, or has not been discussed in the past. And it looks, as a lot of neuromorphic engineers have mentioned here, that spikes carry the notion of time intrinsically. They don't have to think about it, so they're very happy about this. So this notion of time, as physicists talk about space-time, is probably exceedingly important. It appears in dynamical system models. Control theorists tend to work with this, but not information theorists and not computer scientists.
Yeah, but I would disagree that they can't be validated. I mean, there are strong theories, back to the Leland scheduling theory, that if you load in a computer system appropriately, it will meet its real-time constraints with nearest deadline scheduling. And you can then validate the control system's algorithms using dynamical control theory and validate that a control system implemented on a digital system will in fact be correct.
It would not pass any serious, formal test.
I don't know what you mean by a formal test,
you would understand in validation of programs.
Yeah, those people who flew here on aircraft undoubtedly flew on aircraft whose control systems are running on digital computers.
I understand, but every time you take the aircraft and you know the theory, you wonder whether you're going to arrive at the destination.
So, all right. I think the key point, certainly abstracting from what I've heard here today, or not today, but over the last few days, is that the way the timing of spike trains seems to be a critical aspect of how the brain encodes information, and we don't really have a counterpart to that in the way we think about conventional computing. And so perhaps there's something really powerful there that we just don't fully understand yet.
I mean, I think in terms of neural networks, it's a data representation. I was just having this debate a little bit earlier, in that, in a sort of deep learning network, we represent an activation by a code. I won't even say a number, but a code, and we use that code to encode the intensity of a stimulus. A spike train encodes an intensity of a stimulus over time with a number of spikes with a certain frequency. And so I'll disagree with something you said, that spike trains are inherently efficient. They're actually inherently horribly inefficient for two reasons. One is it's a unary encoding of intensity. So to represent something that's 1,000 times stronger, I need 1,000 spikes rather than 10 spikes. And the other is that it's a toggling representation, whereas in CMOS, every time I change the state from high to low, I dissipate power. So in fact, it's much less efficient to represent something with a spike train where I'm toggling up and down than it is to represent it with a continuous code word.
So again, experts in the room, so correct me if I'm wrong. The key thing about spikes is that they're a sparse encoding, and sparsity is a good thing.
Sparsity is a good thing, but you don't need spikes to be sparse.
There are other ways to be sparse, for sure. Yeah.
I think the issue with spikes is it's an evolutionary constraint. I mean, there's a beautiful book called Principles of Neural Design by Laughlin and Sterling, where they ask how much energy does a bit cost to move around in the brain. And if it's diffusion of transmitters through the synaptic cleft, it's just a few kT, not much, but it's slow, right? If it's propagation of passive action potentials through a dendrite, it's a little bit more. It's like thousands of kT, but it's a little bit faster. And then the spike it costs a lot of kT, right, to transmit a spike, but it's incredibly fast. So when evolution is computing simultaneously with molecules, with passive potentials, and with actively generated potentials, and I think that's why we have spikes. I'm not entirely sure that there's an exceedingly good computational reason for having spikes, as can be seen by the avoidance of spikes in neuromorphic hardware more generally. And spike timing is preserved in the sensory periphery, but there's less evidence that it's very, very well preserved deep in the interior of the brain, far from the sensory periphery. The hippocampus is a bit of an exception with phase precession and so on, but anyways,
so,
that's my 2 cents.
I mean, I think this conversation, to go back to what Wolfgang said, I think you can't actually, what's important related to what you just said is learning is critical in this, right? When we talk about neural codes and we talk about spike times and all that, the reason, I don't think we can abstract away from the fact that the brain is updating its codes in many, many areas. Now, we talked about a little bit, the grid cells may be a special case. They're closer to a binary code where you don't want to be shifting the representations. But deep in the hippocampus, deep in a number of regions, you want to update the codes. And the reason you have a sparse spiking code may very well be coupled to the ability to update that code and change it dynamically within milliseconds or within days. And to simply think of, okay, well, spikes are energy efficient, or unary code versus binary code, they're offering something else, and I think that something else is that they're malleable in a way that's different than what we do with conventional computers.
There's a reason why on my slide I said they were important, or maybe not. There's not consensus in this room for sure.
I don't know why a spike would be more or less, if I want to make a synapse, for lack of a better term, which is basically a variable weight multiplication of an input stimulus to produce an output stimulus, perhaps with a nonlinear function involved. I could make that as plastic or as non-plastic as I want with a continuous representation or with a spike. I don't see why the spike representation makes it more plastic.
So it may not make it more plastic, but I think you call out spikes for being unary. And I would argue unary is easier to do learning on than binary, simply because if you want, it's kind of analog in its representation within the time domain. And so if you want to make a spike, spike time represent something a little bit more than something that already was. You just move it a little bit further out in time or a little bit back in time, as opposed to a binary code where you're actually having to figure out which bits you need to flip for a given update. It's a subtle, and maybe a little subtle thing, but I think that unary coding does add something fundamentally different than when we think about binary codes.
So I guess I'd like to follow up on Wolfgang's question and point and his comment. And one way in which von Neumann computers, one thing that distinguishes them is that instructions and data are stored in the same way, right? It's instructions and data are all these numbers that are pushed through the system. And in neural systems, we don't exactly know where memory resides. We think that it's probably local to the computation as well. So there's a circuit. The wiring of the circuit dictates what computation the circuit performs. But also, since the units are sort of individually more memoryless, it also is the recurrent circuitry and the circuit that does memory. And I think trying to understand how it is that you can have the same weights that determine computation, and at the same time you have a demand on the weights to have memory in the same system, and then you add to that the complication that activity in the circuit or pulling up a memory then drives activation, which through plasticity rules is going to alter the weights and the circuit. I think that's a question we've just barely begun to grapple with. How is it that you can have a system where you're storing memory on the same weights that instruct the computation, and each time you do something with it, it changes, right? And I think that's definitely a place where we have to be thinking about, and where there are going to be a lot of contrast with the von Neumann architecture.
I actually had a question, maybe a little bit more on the earlier point about the spikes, which is when we keep talking about spikes as being very energy efficient, maybe the question I want to throw out is, do we really mean that for a biological system? Because the cost, the biological voltages, if I remember, and maybe somebody can correct me, are more on the order of 100 millivolts. So, in that case, yes, maybe it's an incredibly energy efficient way to transmit information in a biological system, but we're not really trying to make a biological system. We can't. So for our system, where the cost of charging is much higher, and where we try to ensure that a spike that gets through with 100% reliability, and our brains misfire constantly, and still somehow we error correct and come out with a coherent answer. But for our systems, the systems we're trying to design, maybe the energy cost of a spike is just a lot higher than it would be in a biological system. And the other question or point I want to kind of make is I've really been on the anti-spike camp for a long time. But I have to admit, yesterday, I was hearing from Giacomo's talk, a lot of the different ways that you could really encode information in a spike. So I think it's not just a matter of sending out spikes which represent just intensity or which represent just a rate code. That it seems to me like that we could design much more efficient ways of transmitting the same amount of information rather than representing it as a spike. But if we could cleverly really understand how the brain encodes this information with all these different kinds of coding schemes, maybe that's where the key is. And we don't necessarily have to mimic that with a train of spikes, but we could figure out our efficient way to do that in the kind of hardware that we can design, since we can't design exactly the way a system like the brain. It's just not possible.
Yeah, I think it's a really good point. I think the spiking system in the brain has evolved because of a certain set of cost and feasibility constraints that biological systems have. And I guarantee you, if your goal is to transmit some information from one place to another electronically, you would not use that as an energy efficient way. If you get an information theorist to come up with a coding scheme, they would come up with something very different because it's a different set of costs and constraints.
Yeah.
I have read a study. I don't have the reference right immediately, but I can look it up after this is over and give it to anyone who wants it, that the metabolic cost for moving a spike is 1 to 2 orders of magnitude higher than charging a CMOS line for the equivalent amount of bits moved. So I think we need to be cautious about saying that spikes are an incredibly efficient thing. The incredible thing about them is that the organization of the brain makes good use of them, not that they are more efficient than the equivalent in CMOS.
Okay. Let's go to the back.
Yeah, just a different comment. Basically, until now, most of the information representation in computers has been done by sampling waveforms in a space domain, if you like. And what we started doing with spikes, essentially we started representing information in the time domain. So it's a space-time swap, if you like. Now, if you look at power budgets, all the time there's pressure to push them down. If you take now, let's say, supply voltage of 1 volt, and you would like to represent information with 20 bits precision, you have to be able to measure a microvolt, which is essentially not possible in commodity environments. Okay, it's just out of question. But as we move into nanotechnology, it's much easier to measure time than to measure space. And as a result, there's a very natural push now from a technology standpoint, as we go deeper and deeper in nanotechnology, to measure time, because it's easier to do than measure space. And it appears that biological systems, they are there. Because, you look at a synapse, you see, a gap of 50 nanometers. And so this is nanotechnology. It's as if the two actually are converging, meaning nanotechnology and biological systems as, we know them. And so there's a very strong argument, historically speaking. In the 30s, we had analog representations, then the digital representations came in. It was through sampling, and sampling in the space domain, and we moved away from the tube-based technology to transistor technology. And as we move into more and more into nanotechnology, it's now more natural actually to measure time than measuring space. And that might be actually a key component into making, quote unquote, the decision whether you go with one technology or the other. Although, as you said, strictly speaking, they appear to be, at least conceptually, at the same level.
I'll mention when I started the work I was doing, I was trying to do it using analog representations, looking at spikes, couldn't find a way to do it, but I view this digital thing I'm doing as a sort of interim implementation of a programmable approximate computer, and if analog techniques, if anybody thinks they know how to do it, I believe there's a 10x or 100x improvement that could be done in a better implementation of the ideas I've presented. I would love to hear anybody who thinks they know how to do that.
Yeah, I'll say I agree with the observation that it's actually much easier to represent great precision in time than it is in, for example, voltage or current values. Actually, time is the one thing we're able to get down to a few parts per million on. But if you look at different things you have to do, if you have to operate on data in electronic systems, you typically want to do that in the voltage or current domain. It's just easier to do the operations, whether it be digital or analog, by having everything together in one clock cycle and do a simple computation. That's what our technology has evolved to do. If you're moving data, most people actually use both dimensions. So if you look at most state-of-the-art communication systems, they encode information in magnitude and in phase. And so they're taking advantage of being able to use both dimensions of voltage and time with each symbol. So if you look at a typical, for example, cell phone encoding scheme, which might be 64 PAM, it's got both an I and a Q component. So you're encoding information in phase, which really means the time domain as well as in the voltage domain.
So I think this is actually one of the key points is kind of how do you actually use the time information and spikes. So I agree kind of what you said. If you're using a unary rate code, spikes don't make sense. It's very inefficient. But my understanding is that the brain doesn't use that. Maybe at the immediate you'll have a rate coding, but it quickly gets translated into some sort of a sparse distributed representation where you're no longer using that unary rate code. And so then that's kind of where the spikes become efficient. It's when you change to this different coding method. So I think that might be kind of part of why using spikes can be useful.
So maybe just one comment to follow up on that. I think one of the key things is how is the information really represented? All the conventional techniques we've used so far are symbolic manipulation and symbolic manipulation only. And you have to have your symbols be accurate to be able to do the computation you want to do. Potentially in the brain, it's not a static symbol, but it's a spatiotemporal representation of the information, and that's really the core benefit of that system. It's not just the energy, it's not just the time, but it's the difference of how information is represented, processed, stored, recalled, using that kind of an approach rather than just a static symbol.
If I can add to that, I think I mean, some of the things that we're discussing would really cancel each other out. It would be really clear that having spikes is actually efficient if you think of spikes as packets. And if you think of asynchronous logic and sending out packets, already it's the most optimal from the engineering point of view. You know, pulse frequency modulation and sending asynchronous packets is one of the most optimal energy efficient way of transferring data. So it is somewhat compatible with the solutions that the brain found to transmit signals long distances.
I had a question for the panel on, there seems like there's been a lot of discussion on the locality constraints of the brain and for the approximate computing systems for the, presumably the error correcting codes, although maybe not in the sort of general purpose Hopfield nets. At some level they have to be local as opposed to global error correcting. And I was just wondering if there's a sort of general consensus on a theory for how to decompose an arbitrary problem that, for example, that the brain appears to be able to solve into locally constrained computations, right? I mean, when we don't have, most people don't think the brain has a central controller in the sense of a CPU, and so somehow we have to break everything into something that's locally computable without some sort of global reconciliation or obvious global reconciliation. And I was just wondering if there's, in all the separate fields, whether there's a theory of how to do this efficiently so that it's more compatible with the kinds of local memory processor units that we might be moving towards, at large scale, whether they be approximate computers or next generation GPUs.
Are you talking about problems related to how the brain works or the general space of computing?
I'm really just talking, about the general space of, if your computer is organized the way that yours is, Joe, or, the CPU, your specialized CPUs are there sort of general theories for here's how I can take a sort of arbitrary problem statement and put it into that architecture where it's computable, right? I mean, presumably the brain is doing that all the time. As I formulate a problem, I don't really have the option to go to like central, to go to my, to go to my RAM and go to my hard disk and cache things in various places the way that a von Neumann machine would.
I mean, I could certainly obviously be wrong, but I tend to think of it as similar to the general space of programming where it's like somebody says, my mom says, well, how do you program a computer? It's like, there's a lot of different ways, depends on the problem. There's courses and books, and it's just a big space of knowledge, and it's a mess. And so...
But in terms of locality, which I think is what you're asking about, it tends to naturally fall out when you draw, a signal flow diagram, in a, vision system, for example. You have input images, and then you've got, convolutional layers, and ultimately you have fully connected layers, and then you have downstream logic that acts on the output of the network to make decisions. Maybe it feeds a mapping, a SLAM process, maybe it feeds a control process that's doing path planning. And as you draw the signal flow diagram, you can draw boxes around things and look at the number of bits per second that flow between them, and also talk about the total amount of state of both activations and weights that need to be in each box. And that drives the localization. I mean, many of these algorithms just naturally are local because there's a small number of bits, of the activations flowing between boxes and lots of bits in the box that never have to move.
So certain problems it's relatively easy to see. Other problems, talk to quantum chromodynamics people and they say, I have this 5-dimensional structure, how am I going to fit it into your 2-dimensional mesh? It's like, well, I don't know. It's going to take some thinking. So I think it depends. A lot of the current problems in vision and speech and learning seem to fit nicely. I don't know if it's an accident that the cortex is sort of a roughly 2D-ish thing, but in general, computing's arbitrary, and I don't know how you do it in general. It's a good area for study. You should fund a bunch of software projects.
I think the learning part, though, doesn't always fit modularly into, because if you do end-to-end training of a deep neural, then you have to propagate signals from end to end. And I think that's one direction where we could make some innovations where you can try to come up with local topologies and semi-local learning rules where you don't need to propagate information from end to end, yet you can still solve a global problem. Just in general, like parallel optimization theory, there are some cases of that, like, things like consensus optimization and ADMM and things like that, that, for example, Steve Boyd is popularizing and working on. They have some ideas there, but I think we need an explosion of ideas there in order to really leverage the parallelism offered by neuromorphic computing.
So with all the excitement and attention to deep neural networks, what are the limitations, what they cannot do, and what are the applications that are waiting for different neural architectures?
So you said, what can they not do? And
yeah, I mean, so we need
they're really bad. They're really bad, for example, at physical simulations. I mean, if you look at people who want to run a climate model, it requires propagation of state through a set of differential equations over time. And this is one of these examples where you are subtracting two big numbers to get the difference, which you then add to your state to move it to the next time step. And you can't do that with a neural network, right? It's not accurate at doing these sort of time integral 3D model types of computations. That's not what it's designed for or good at. But it tends to be really good at any recognition task where you have a bunch of input sensors with information on it, and you want to build feature recognizers to make sense out of that.
So, I mean, it was a repeating theme that we need better, different neural theories. And I was wondering, okay, we have deep neural networks, and they're doing quite fine on the problems here actually mentioned. And what other neural architectures we need to actually explore?
So I think it's 12 o'clock. I don't know if you want to finish, if there's a follow-up to that question, and then we can end the panel. Did anyone want to have a final comment on that?
Can I have a quick follow-on to that?
Yes, please.
Question? I wanted to ask, how pervasive do you think neurally inspired processors are going to become in the future? So in other words, are almost all RISC processors going to have a neurally inspired processor as a co-processor next to them, or are these going to be fairly niche, specialized applications, systems?
I think that they're going to be really prevalent in all input of real-world data. In that anything sensory, whether it's sort of speech or still images or video or radars or LiDARs or any kind of sensor, is going to have immediately behind it a neurally inspired chip of some kind. But I think deeper parts of the system are still going to rely on conventional computing to do kind of very non-neural tasks dealing with finite states and physical models of systems and things that often have to be represented in higher precision and more exact computation. So I don't think either is going away, but I think dealing with sensory data, there's no better way of doing it.
Yeah, and I think dealing with sensory data is going to become increasingly important. Machines are going to be dangling off people's ears and in your buttons, and they'll want them to understand speech and see and think a little bit. And so I think if you look at the number of machines in the world, it's going to be, they're all essentially all going to have perception and related capabilities.
Yeah, I'll agree with that, right? I mean, pattern recognition is one of the, it's a ubiquitous problem. It's a problem that we're good at solving as humans. Our machines haven't been good at solving those, but now that we have architectures that can solve pattern recognition problems, if there are cheap and efficient solutions for it, they're going to proliferate. Fields as diverse as astrophysics, high energy physics for detecting particle events, for looking to see whether this restaurant matches the restaurant you're looking for from Google Maps. I mean, all of these things involve some form of pattern recognition problem, and I don't see any reason why they wouldn't proliferate.
Okay, well, let's thank our panel.